Okay, so let's dig in. You'll have to do this as well. So we're going to use right-hand endpoints to find the exact area under the curve. So first step is finding the delta x. So that's 3 minus 0 divided by n, so 3 over n. So next, I want to make a number line to talk about. It's going from 0 to 3. So each of my rectangles have width 3 over n. So this x value will be 3 over n. Then if I make another rectangle of width 3 over n, this will be 2 3 over n's. Then this is 3 over n. This will be 3 over n's, dot, 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 dot. And this is getting us to 3, so that's going to be n 3 over n's. All right, so let's talk about setting up r sub n. Okay, so rectangle number 1 here, right-hand endpoint is going to be this term here. So it'll be a width of 3 over n, and then I'll have f of 3 over n to get the height. Plus, second rectangle will be width of 3 over n, and between these two edges, this is my right-hand endpoint. So f of 2 3 over n's. Plus, and then again, rectangle number 3 has these two edge points, so I'm going to use 3 over n, f of 3 over n's, dot, 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 dot. Okay, so I come to the last rectangle, rectangle number n. The right-hand endpoint will be this one. So I have 3 over n, f of n 3 over n's. All right, so let's write this as a sum. So again, what I want to do is I want to make up I equal 1 to n, so that when I plug in I equal 1, I get that. I equal 2, I equal 3, I equal n. This is usually the nice one to look at to get a feel for the pattern. So I see this is going to be 3 over n, f of I times 3 over n. And just make sure it works with all the rest of them, and it does. All right, so now we're going to use the function. So this is something we haven't done in all the steps that I've been building up to. So x squared minus 6 is the function. So let me bring this over here. So 3 over n. Okay, so now instead of f of this, I'm going to be substituting this everywhere there's an x, correct? So I'll have I times 3 over n all squared minus 6. So that's this, f of that quantity. Oops, and I forgot my I equal 1 to n. All right, so I equal 1 to n, 3 over n, and then I'm going to multiply this out, so I get 9i squared over n squared minus 6. So let's even take that a little further. So I'm going to pull that 3 over n on the outside. And then I'm going to separate it around the subtraction. So 9i squared over n squared minus 6. I equal 1 to n. All right, so let's even go further with the simplification. So 9 and n squared can come outside of this sum of I squared minus I equal 1 to n of 6. Okay, so this is where those nifty formulas come in. Remember? So this is, so looking back, whoops, like that. Looking back in your notes, you can look up the fact that this is equal to n times n plus 1 times 2n plus 1 all over 6. And then adding up 6 n times is 6n. All right, so now that's just the adding up of the n rectangles. So to get the exact area under the curve, 0 to 3, x squared minus 6x, I'm going to take the limit as n goes to infinity of this quantity. So let me bring it up here. So 3 over n, oops, because I don't need that parentheses there. Let me do that. So 3 over n out here. And let me join some stuff together here. So 9n, n plus 1, 2n plus 1, all over 6n squared minus 6 over n. Okay, so let's multiply that 3 over n inside. So I get 27, and I'm just going to go really slow so I don't make any mistakes canceling. So I get 6n cubed, and then if I multiply 3 over n times 6 over n, I get minus 18. All right, so let's go to working on finding the highest powers from this term here, because this 18 is just nice, ready to go. So I have 6n cubed from the denominator. On the numerator, I would have 27 times 2, so 54, n, and n, so n cubed. So from these, since these n cubes cancel, I get 54 over 6 minus 18. That is the exact area under the curve.